Hi, welcome back to the session. Last time we had talked about the confidence interval, right? The interval of mean, the population mean, when the population standard deviation is given. Right, the idea is we have a simple random sample of size n to get the idea or to get the estimate of the population mean. Right, procedures was written last time, like to check the conditions which either population is normal or size is big enough, could be both, and to find the critical z-score corresponding to the confidence level, which, well, you can find it on your table as well, that 90% we use 1.645, 95% z-score of 1.96, and 99% we use 2.58. It could be 2.575, but 2.58 is nothing wrong. Could be also acceptable. Then evaluate the E and find the value x bar minus e x bar plus e after we take in everything, right? All the information from the question. Right? Then at the end, we could draw the conclusion to say about how many percent of the confidence that we sure the true mean of the object is between such two values, right? Such lower limit and upper limit two values. So let's see the example, right? Let's see the example. A study got a simple random sample of 106 healthy adults that has a mean of temperature, a body temperature of 98.2 degrees Fahrenheit. Also, we know that the population standard deviation was known to be 0.62 degrees Fahrenheit. That was what we know for the population standard deviation. Right, so basically, that's the thing we know from the population, right? The shape of the distribution of the body temperature, pretty much. Well, what can we conclude about the mean body temperature of healthy adults under 95% confidence? Right, so that is the full question. It provides much information as we need to know. Or even though the question didn't say, well, what's the population follows, what distribution it follows. But the sample we get is big enough, right? It's 106. And we have a mean of 98.5 from that sample when we read the first sentence. And when we read it, we get that the first sentence is get a random sample of 106 healthy adults and has the sample mean temperature, mean body temperature of the sample is 98.2 degrees Fahrenheit. Right, the mean body temperature of the sample is 98.2 degrees Fahrenheit. Also clearly states that the population standard deviation is 0.62 degrees Fahrenheit. That's what's given as well. Right, and asking for the mean body temperature of the population and the 95% confidence. Right, the confidence level is 95%. So the condition, of course, here is satisfied, right, such that the population, we don't know the population, but such that we know the population standard deviation is 0.62. And also the sample size is large enough that it is 106. Right, so when the population standard deviation is given and the sample size is large enough, we can use the z-score. And what we provided is sample mean 98.2 degrees Fahrenheit, population standard deviation given to be 0.62. Also 95% confidence level, as well what we know is the sample size is 106. Right, that full information listed over here is what we know. Right, from the 95% confidence, we can know the z-critical, z-crit. The critical z-score from 95% is 1.96. Okay, it could be found from the normal distribution or standard normal distribution table, or the z table, you can find it. Right, the critical z-score for 95% confident is 1.96. Could be direct to that. Then the next step, we can find the E. The margin of error is the critical z-score times population standard deviation over the radical n. Well, you can use a calculator to find this number out. And if you want, you could keep more digits if you want, but 2 or 3 digits will be good enough. 1.96 times 0.62 divided by square root of 106. If you want to keep in 3 digits, that is 0.118 of the margin of error. Right? So we see the standard deviation of the unit of degree Fahrenheit, the sample mean of the unit of degree Fahrenheit, and then the margin of error will be the same unit of degree Fahrenheit. Then to find out 2 numbers, which are the limits of the interval, the lower limit use the sample mean minus the margin of error. And the upper limit will be sample mean plus the margin of error. And last but not least, actually the more important thing is to write down what these numbers represent. After we find the interval, what they are. We know the population mean will be in the interval from 98 between these two numbers. That is the interval, but what that means? Right, that means we're 95% sure that the object was asking the mean body temperature of healthy adults is between these two values. It's between 98.082 Fahrenheit and 98.318 degree Fahrenheit. So we actually do not know what the population mean body temperature of healthy adults is based on this information. But from the information given, we are 95% confident that it is between these two values. We don't know actually where or what value exactly it is, but we are 95% sure that the value is between these two numbers. Right, that is what the confidence interval doing. We give a certain value of level confidence to make sure that, to be sure that we know that it's between these two, but what exactly it is, well, we don't know. Right? But we get an interval that the value should be in between these two numbers. Right? So to do this type of equation, to pulling everything out from the question will be the key. Right? The first thing, all these information listed, then what we need is just follow the formula to do it correctly, right? The point estimate will be the sample mean, and minus plus the margin of error we found it will give us the interval of the population mean. Right? And finally the conclusion will be state clearly what we are doing. Right? Then let's see the next example. Right, for this question here, the GRE score of quantitative reasoning is normally distributed with a standard deviation of 8.5. A group of 25 students recorded their mean score is 150.2. And what can we say about the mean GRE quantitative reasoning score and the 99% confidence level? I usually given a 95%, 99% confidence level for this type of question. Right, and we know the population is normally distributed. Right, so that's the first thing we're looking for. If it's normally distributed, then the central limit theorem satisfies, which means we can satisfy the condition of this type of confidence interval thing. Right? We have a standard deviation of 8.5, which is from the population. We know the GRE score is normally distributed. This population has a standard deviation of 8.5. A group of 25 students, in this case is less than 30, but it's okay. Since we got the population standard deviation and we got the population is normally distributed, has a mean score of 150.2. Then this mean has to be the mean from the sample, right? Because we have no clue about the population mean. Then this mean has to be a sample mean. Then what we also given is want to find the mean GRE quantitative reasoning score and the 99% confidence level. So still, right, first of all, we get the sample mean is 150.2. That's first information we need to take out, which is called the point estimate. 150.2 is the point estimate. Then sample size of 25 is what we know. Standard deviation from the population is 8.5. Right, by reading the question, we already know this standard deviation is from the population. That is very important skill, right? By reading the words out, we need to know that this is the population standard deviation. And at the end, that's 99% confidence. Right, the order to get those is actually doesn't matter, but well, as long as you get all the information, that's good enough. I have 1, 2, 3, 4 informations, as well as the normal distribution, which may be given, maybe not. Then from that, our critical z-score. From that, our z-crit is 2.58. So we can go to the next step to find the margin of error. The E is the critical z-score times the population standard deviation over radical n, which critical z-score is 2.58. Population standard deviation 8.5 over radical of 25. You can use calculator, you'll find the same answer. Right, multiply 2.58 times 8.5 divided by square root of 25. That will give us 4.386. Then we find two values of the lower limit x bar minus e and the upper limit x bar plus e. Right, the x bar minus e, that's 150.2 minus 4.36. is 145.814. That is the lower limit. And we find the upper limit, x bar plus e. X bar is 150.2 plus the error we found, 4.386. That's 154.586. Right, so that is the lower limit and upper limit. So we can write our conclusion, right? What these values are. The mean first is following the interval 145.814 to 154.586. Right, that's what we found for the mean interval where it stays, right? The confidence interval for the population mean what it is. Then write down the conclusion of what this interval means. We have 99% confidence that the mean, what it's asking, the mean GRE quantitative reasoning score. Right, the mean GRE quantitative reasoning score is between these two values. Right, it's between these two values. So those two examples was given the population standard deviation and follow the condition of the central limit theorem. Right, that we can use the z-score as the approximation, or z-score or the normal distribution as the population, as the x-bar distributed. Right, the population, if it's normal, then of course the sample mean is distributed as normal distribution. If we don't know but sample size is big enough, then the sample mean could be approximated as normal distribution. That's what the central limit theorem states, and that's what we are using. Right, the thing is we have to know at least the standard deviation of the population of the original. Right, so some other case, we do not know the population standard deviation. We have only given the sample standard deviation. But the population standard deviation is not given, even though we know the shape that the population is normally distributed, but we don't know the population standard deviation. But good thing is the sample standard deviation is known. So when we got a simple random sample, we can get the sample mean, right? If the population standard deviation is given, then we don't have to worry. But in the case population standard deviation or the sigma is not given, then we could use the sample standard deviation as an approach. But in this case, it's not approach the sample mean to a normal distribution. Another thing is another distribution will be approximated to, right, but still have requirement. As the same requirement as the central limit theorem. The population has to be normal, or the sample is large enough, and of course could be both. Then we can use the student's t-distribution. Well, it is also published by a mathematician, but in the meantime, the magazine he posted, he used his nickname called the student. Then that's what the student comes from. Right? And that is the t-distribution, which on Blackboard you can find the t-distribution critical value table, which is the table A3 uploaded online. Right? You can find it, and we'll talk about more about that distribution, how to find what we need. Right? But for this case, we can see the distribution of t. Right, the first curve below, that's the t-distribution with n equal 3. This one is the t-distribution for the larger n. Right, and when the sample size is increased more and more, it will look more like a standard normal distribution. Right, as the sample size is increased, the sample mean will be more approached to the standard normal distribution, closer and closer to the standard normal distribution. But well, it's still looking differently. Right, so when KC Right, the student t-distribution is different for different degree of freedom, which the sample size is n, the degree of freedom is n minus 1. Since we use the sample mean and sample standard deviation, right? Sample standard deviation, basically. Right, so when we use the sample statistic, right, the n-1 data are free, but when the n-1 data are setted and the sample mean is set, the last one is not free, right? So the degree of freedom for n data in this case, right, for when we use sample or when we use the t-distribution, the degree of freedom will be only n-1. Right, yes, same. Well, it is also the bell shape, but reflects greater variability. Which we can see the density is lower, that means it's spread widely and very widely, greatly, right, greater than the standard normal distribution. Right, greater variability when n is small. N is smaller. It is same as the standard normal distribution, that the mean is at the center 0. Also, when n gets greater, right, the t-distribution is closer to the standard normal distribution. That is the property, right, of the t-distribution. So the critical t-score or the t-score from the population, the t-score will be same as the z-score. In this case, we use the sample standard deviation as an approach of the approximation of the sigma, right, that we get the t-score. Therefore, the shape will be very similar as the normal distribution, and when we find the x bar, when we find the mean will be x bar plus minus the critical t-score times standard deviation over radical n, from which the standard deviation is the sample standard deviation provided, and same sample means in the radical n, and the case when we use the critical t-score is when we do not know the population standard deviation, right? When we don't know the sigma. and we provided the S, right, the sample standard deviation. So the critical value is the critical t, right? So in part of margin of error, we could find the critical t-score first, right? And in a table of the t-distribution, I have to find degree of freedom on the left, and the area in one tail, area in two tail, and so on. The table we have one tail, and on the left we can see the degree of freedom with bunch of number 1, 2, 3, and so on, all the way we get 38, 39, 40, 45, 50, and so on, right, all the way to 2000 large number. Then area in one tail, area in two tail are the rows. A column and a row still use the idea that the intersection will be the thing we want to find. Right, so how to find the critical t-score? Right, so first of all, the degree of freedom is n-1. Right, since we use sample standard deviation as approach, right, and therefore the sample is playing important role there. Therefore, the degree of freedom is n-1, right? When we use the sample and the values are set for the sample mean and sample standard deviation, then the data set itself will lose 1 degree of freedom, right, as we explained. Then, for example, so if we given sample size is 20 and the confidence is 90%, right, so when we get the sample size and confidence level from a question, right, then in that case, we're able to know that, well, that is the t-distribution. Area in the tail, we don't know what it is, but we know the middle is 90%. Therefore, what we can know, right, to find the degree of freedom is area in two tail is 10% or 0.1. And also, we're given the size is 20, the degree of freedom will be n-1, that is 19. Therefore, we go to the table of 19. Area in two tail, we go to 0.1. Then in the intersection of these two values, we are able to find the critical t-score of 1.729. We'll go to the column of 19, we go to the row of 0.1, go down and go right. We're able to get the intersection of the t-score of 1.729. Therefore, the critical is 1.729. Right after we get the t-score, that everything else could be done in this case. Right, let's see another example. Right. N equal 38, 95% confident. So we know two things, right? Area in two-tail is 5%. In other words, is 0.05. Also, the degree of freedom is n minus 1, which is 1 less than the sample size, that is 37. Then we can go to the intersection of 37. Area in two-tail is 0.05. I'll go down from 0.05, go right from 37. That we can find the intersection is 2.026. From these two, we can get the T crit is 2.026. Right, that's how we find the critical T-score. Right, that is a little extra thing when we need to use the confidence interval, but we don't for mean, but we don't know the sigma. We use S and use T distribution as the approximation or as the approach of the population mean. Right, then the extra thing is to find the critical T-score. Now we need to find by ourselves.